let us consider another problem of SHM which is related to rotatory motion. A disk of mass m fixed to a point and its mass is m. Now, a spring is connected to the spring. A string is connected to the string. Spring you can call as constant k. To the other end of this string, mass m connected. A small object of mass m is connected. Now, there is enough friction so that there is no slipping of the string on this pulley. Now, give a small displacement x, down and leave it, then the total system executes SHM. If it moves by x, the extension of the spring is x. Okay. Now, when it is moving down, it also rotates. Let us find out what is the frequency of the rotation of the oscillation of the system. To solve this type of problems, instead of going by force method, let us go by energy method. Okay. What is this energy method? If you look at a spring mass system, let us take example of a spring mass system. If x is the extension of the spring, which is same as the displacement of m, the total energy at any instant of time half mv square plus half kx square, which is equal to constant c. The total energy due to SHM is half mv square plus half kx square, which is a constant, doesn't vary with time. If I differentiate with respect to time of m, 2v dv by dt, differentiation of v square is 2v dv by dt plus of k 2x dx by dt, since the differentiation of constant is 0. When I write the total energy of SHM, the total system, half mv square plus half kx square, if I differentiate with respect to time, anyhow half is common, gets cancelled, 2 also gets cancelled. Now, this dx by dt is nothing but velocity. This velocity gets cancelled. M dv by dt is nothing but acceleration. The rate of change of velocity is acceleration, plus kx is equal to 0, or a is equal to minus k by m into x. So, a is equal to minus omega square x, where omega is root of k by m. So, this is the another way to find the frequency of oscillation by using the energy method. So, whenever you have this type of complicated system, we can easily solve this system by using energy method. I am going to apply this energy method to this system. So, now let us write the energy of the system. The kinetic energy of this mass at any given instant of time, v is the velocity, m is the mass, the kinetic energy half mv square plus the very important is it is rotating. Then the energy of this disk is a rotational kinetic energy, which is equal to half I omega square. Of course, this omega is the angular velocity of this disk plus half kx square is equal to some constant c. The total energy of the system is the kinetic energy of this mass, the rotational kinetic energy of this pulley, or pulley usually it is taken as a disk, plus the elastic potential energy stored in the spring. Now, if I differentiate this half m 2v dv by dt plus half I. What is I? The moment of inertia of the disk about the central axis, that is mr square by 2 to omega d omega by dt plus half k x square is 2x dx by dt, which is equal to 0. Okay. The total energy consists of 3 terms. I am differentiating each term with respect to time. So, differentiation of a constant is 0. Anyhow, we can cancel half. This 2 also gets cancelled. Fine. And mv dv by dt is nothing but acceleration. M is the mass of this small object connected to the string. V dv by dt is acceleration. Okay. And we know that this v is equal to r omega and omega is equal to v by r. V by r. What is this r? Radius of the disk, where r is the radius of the disk. What is d omega by dt? And d omega by dt is angular acceleration. A is equal to r alpha. So, alpha is angular acceleration. Angular acceleration alpha is equal to a by r plus k x into v is equal to 0. Now, everything is converted angular quantities into linear quantities. V is anyhow common, gets cancelled. So, m, there is I is here, plus I is there here. This I should be here. M a plus I a by r square plus kx is equal to 0. So, finally, we get an expression where acceleration a is equal to minus omega square x, where a is equal to minus omega square x. This equation proves that acceleration is directly proportional to displacement directed opposite, which is the basic condition for simple harmonic motion. And what is I here? Where I is the moment of inertia of the disk, which is nothing but mr square by 2. So, I can be written as m r square by 2. I am taking this pulley as the disk. So, you substitute I value, from that you find out the angular frequency of oscillation. This omega is the angular frequency. Of course, this omega is different. This omega is the angular velocity of this. So, this is one of the SHM system which is connected to again rotatory motion. Let us take up the another system which is connected to rolling motion. Let us say a disk a disk of mass m connected to a spring of constant k, the other end of spring is fixed. The other end of the spring is fixed, and the disk is placed on a horizontal rough surface. This disk, okay, this disk or maybe sphere, depends on the given shape. Okay. There is enough friction. There is enough friction between the disk and the horizontal surface. There is no slipping at the point of contact. There is no slipping at the point of contact. Now, give a small angular displacement. Give a small the angular displacement and leave it, then the disk executes simple harmonic motion. So, you have to find what is its angular frequency. Once you know the angular frequency, you can find out its time period or frequency. Now, what is the difference between this case and a previous case? Here, in the earlier case, no doubt the disk is rotating about its central axis, but now the disk center of mass has not only translatory motion, it also rotatory motion. So, the combination of translatory motion and rotatory motion is called rolling motion. Okay. Now, we know that in case of a rolling, the energy of the object is of mv square plus of I omega square. In case of a rolling body, translational kinetic energy is half mv square, rotational kinetic energy is half I omega square. Here, what is this v? Where v is velocity of the center of mass, and in case of pure rolling, v must be equal to r omega, where r is the radius of this object, omega is the angular velocity. If I substitute omega in place of omega v by r, the rotational kinetic energy of I omega space of mv square together will or you can write the kinetic energy of a rolling body is half mv square into 1 plus k square by r square. You may ask, what is this k? Where k is called radius of gyration. Okay. In place of moment of inertia, I am writing m k square. Okay, this small m we can write, where k is the radius of gyration. I is equal to mk square, where m is the mass. So, in place of I am writing mk square, in place of omega I am writing v by r. So, I am getting the kinetic energy of a rolling body is half mv square into 1 plus k square by r square, where r is the radius of the body, k is the radius of gyration. So, I am going to use this formula when the body is in rolling motion. So, that is a extra term will come here. Now, I am going to write the total energy of the system. So, disk is in rolling motion, its total kinetic energy is half mv square into 1 plus k square by r square. Suppose if only rotatory motion, only half I omega square, only translatory motion, half mv square. So, since both are there, I am writing this plus, when it is moving, there is a compression of the spring x. The potential energy stored in the spring is of kx square, of kx square. This is the C. The total energy of the system is kinetic energy due to rolling motion plus potential energy half kx square, which is a constant. Now, if I differentiate with respect to time, since total energy with respect to time remains constant, of m v square differentiation is 2v dv by dt. Differentiation of v square is 2v dv by dt. Anyhow, 1 plus k square by r square is constant. Keep it constant. If the body is a disk, k square by r square is half, ring 1. If it is a sphere, 2 by 5, solid sphere 2 by 5, hollow sphere 2 by 3. Of one more thing is this k is, okay, let us say this k is radius of gyration k dash I want. This k is spring constant. You may confuse with 2k's. This k is radius of gyration, this k is spring constant of k 2x dx by dt is equal to 0. So, if you differentiate this with respect to time, we got an equation. Now, simplify this. Anyhow, half is common. Here v, dx by dt is again a v, gets cancelled. Okay. And dv by dt is acceleration. So, this expression we can simplify, we can write a is equal to minus omega square x. The acceleration is equal to minus omega square x. You can take omega from this expression. Omega is nothing. From that omega you can find out either time period or frequency of oscillation. Okay. The basic idea is write the total energy expression, differentiate with respect to time, we will get the required condition for simple harmonic motion, that is A is directly proportional to x and directed opposite displacement. Okay. So, this is the one important problem where SHM is connected to rolling motion.